Hello everyone, I'm Dongxiang and welcome to our talk, the Unix domain socket, a hidden door leading to privilege escalation in Android ecosystem. First, let me introduce our team. We belong to the Baidu AIoT secure team and focus on the security of the Android and the Linux platform. Our duty is to discover zero-day vulnerability and explore possible defensive solutions. Here is the agenda for our today's presentation. Firstly, we will briefly introduce some basic knowledge about the Unix domain socket. Secondly, usage scenarios. You may wonder where the Unix domain socket is used in. This section will answer this question. Thirdly, common vulnerabilities and case study. Normally, a third-party application can't directly connect to a vendor socket service. Thus, vendors often ignore their security, but access control can't solve all security issues. In these two sections, we will elaborate on this. And in the end, we will introduce some automated analysis methods. Let's first understand some basic concepts. The Unix domain socket is also known as UDS or IPC socket. For convenience, we will use the name UDS later. A UDS is a data communications endpoint for exchanging data between processes executing on the same host. As shown in the figure, its API and the communication mode are very similar to the network socket, but rather than using an underlying network protocol, communication occurs entirely within the kernel, so it's more suitable for the local IPC. Types and namespaces. Like the network socket, the UDS also has three types: socket stream, socket diagram, and the socket sequence packet. The stream socket is stream-oriented, works like a pipe, and the diagram socket is datagram-oriented. It's similar to a message queue. The sequence packet socket is connection-oriented, but also preserves the message boundaries. And each UDS can use a name to identify itself. You can use the file system namespace and bound the name to a file system path, or use the abstract namespace, which is independent of the file system. And using netstate or ss command, you can list all Unix domain sockets on a device, and you can see their types and names. If a name starting with @ means it uses the abstract namespace. Android provides many encapsulated APIs to use the UDS. Knowing these APIs is very helpful for reverse analysis. At the Java layer, you can use local socket and the local server socket to create a UDS. The local server socket is the most common API. It encapsulates multiple low-level APIs, such as bind and listen. It can create a server socket, listening at a specified name. Indeed, most Unix domain sockets are created in the native code because there are more fine-grained APIs. The UDS facility is a standard component of the POSIX operating system, so we can use all POSIX socket API. Just set the domain to the AF Unix. On the other hand, we can use some encapsulated APIs, such as socket local server and socket local client. They are more convenient, but not included in the NDK. Access control is a key point. There are many ways to do access control for the UDS. First, if a UDS is bound to a file system path, then we can use the file permissions to control who can write the socket file. This is the easiest way. Secondly, the getSock_opt API can get a client's credential, which is the UCRED structure. It contains the peer's PID, UID, and GID. Then you can use this information to determine whether to deny the request. In practice, Using SELinux to do access control is the most common way. The SELinux has good support for the UDS. There are 3 related classes: sock file, Unix stream socket, and the Unix DRAM socket. The sock file class is used for the socket file object, and the rest are used for the process object. We can control which domain can write to a specified socket file. Like policy 1 in the figure, it means all domains are allowed to write the logdw socket file. We also can control which domain can connect to a socket created by a specified process. Like policy 2 in the figure, it means all domains are allowed to connect to the Unix DRAM socket created by the logd process. In addition, Android also provides some macros for setting SELinux policies. You can find a lot in AOSP. Next, I will introduce some usage scenarios of the UDS, which will help us think more systematically about this attack surface. We analyzed the UDS services on various devices one by one and summarized the most important scenarios. These usage scenarios can be divided into categories. The first is diagnostic tools, such as log management tools and exception management tools. The second is complex hall modules, such as GPS. Let's see some real-world examples. The first is log management tools. Logs are the most important information for troubleshooting. In an Android device, there are usually 2 logging systems. One is the Android standard logging system, and the other is the Windows logging system. Let's first look at the Android standard logging system. The logd daemon is a call, whether using log API in an application or using logcat command. All requests are handled by the logd, just like the architecture in the diagram. Logd contains 3 modules. Each module listens on a UDS to export the interface. Then you can write logs to the logdw socket, read logs from the logdr socket, and send commands to the logd socket. And this is also how logcat command works. The Windows logging system is more complicated. Android contains many hardware modules. If logs of hardware modules are all printed to the standard logging system and mixed with the application's log, it will be difficult to troubleshoot hardware issues. So a better way is to develop another logging system. The diagram shows the architecture of a Windows logging system. The top layer is a management application, debugger UI. System developers can use it to manage logs. And below the debugger UI is various log daemons, and they are responsible for collecting logs of different modules. Mobile logd is the most important one. It can collect kernel modules log. Each daemon listens on a UDS to receive commands sent by the debugger UI. The next layer is about how each daemon gets logs, and the different modules print logs in different ways. Kernel modules usually use the virtual file system, and the user space processes usually use the Unix domain socket. Exception management tools also use a lot of Unix domain sockets. In AOSP, the Tombstone D and the system solver all use the UDS to receive exception information, but our focus today is not on them. Many vendors would develop additional tools to enhance the existing exception system, such as AEE, Android Exception Engine. AEE is a powerful tool. It can cache exceptions thrown from the Java code, native code, and even the kernel code. It also provides various supporting tools, such as RTT, which can dump runtime information of a process. As shown in the figure, it contains an exception table. It is convenient to query which module occurs an exception at what time, and you can get full backtrack information. The full implementation of the AEE is extremely complex and is a closed source software. Fortunately, we only need to focus on the UDS part. As shown in the figure, the AED daemon listens on 3 Unix domain sockets. The AED and AED32 sockets are used to receive exception information. The RTTD socket is used to export some interfaces for dumping runtime information. The AEE has instrumented the activity manager service and the crash dump. So when an application exception occurs, the activity manager service will connect to the AED socket and report the exception information. When a native exception occurs, the crash dump will connect to the AED32 socket and send the tombstone file path. The tombstone file holds the exception detail. Another usage scenario is the hardware abstraction layer, as shown in the diagram. The HAL defines a standard interface for hardware vendors to implement, which enables Android to be agnostic about low-level driver implementations. A complex HAL module usually consists of 2 types of process. One is the HAL services, used to provide standard interfaces for the framework, and the other is daemons, responsible for implementing specific functionality. So what does this have to do with the UDS? The answer is the UDS is the main IPC method between these processes. Let's look at an example. The diagram shows the architecture of a GPS module. It contains 2 hardware vendor services and 3 daemons. 2 services provide the framework with standard interface to use GNSS and LTE partitioning protocol. And the core functions are implemented as these 3 daemons, in which LBS DBG is responsible for the GPS module's log. MNLD is responsible for GNSS related functions. And AGPSD is responsible for AGPS, using network information to assist partitioning. Each daemon provides some low-level interfaces through the UDS, and the processes in HAL cooperate through the UDS. And this communication model is very common in hardware modules. So far, we have seen some UDS services. We also analyzed many other UDS services, and they have some common features. First, they are usually run in the high-privileged daemons, either system or root, and are responsible for some sensitive tasks, such as reading and writing system files, talking to the driver. Since they are valuable attack targets, and UDS is a good attack surface. The second is an important but easily overlooked feature. These services are usually a node of a complete data flow diagram, as shown in the figure. In complex module, various IPC methods connect multiple processes at different layers. The UDS is just one of them. There are many paths to attack a UDS service. You can use this upstream node to forward the attack payload, and which will work in multiple scenarios. Next, I will introduce some common vulnerabilities we found in vendor daemons. As shown in the diagram, a typical UDS server usually has 5 states. Each state may have different problems. The first is to initialize, enable different functions according to the configuration. Sometimes misconfiguration can cause serious issues. Then is to listen and receive requests. There may be a problem of invalid access control. And the next is to pass the request and forward it to the handler. There may be some memory corruption vulnerabilities. Last is to handle the request. There may be some logical vulnerabilities. Let's go into some more details. First is misconfiguration vulnerabilities. They are common in the diagnostic tools. There are two common mistakes, and they all result in some dangerous interfaces to be exported. The first is packaging configuration mistakes. It can cause internal debugging tools to be packaged into the distribution room. The second is run configuration mistakes. It can cause diagnostic tools to run in the wrong mode. For example, v11836 is an information leakage vulnerability. The downstream manufacturers configure AE to the debug mode and causing some dangerous interfaces exported. And the attacker can use these interfaces to obtain some sensitive information. But in normal mode, these interfaces are only available for the root privilege. Invalid access control. As we mentioned earlier, UDS service usually undertake some high privilege tasks. Therefore, it must be guaranteed that the untrusted application can't access these services. But in practice, many access control strategies are invalid. There are four common mistakes. First, downstream vendors may disable SELinux. Doing so will shorten the development cycle. And fortunately, this situation has improved now. Second, just performing authentication in the client SDK. But an attacker can bypass the SDK and directly connect to the service. Third, using wrong authentication methods, such as obtaining the client's process name and then checking whether the process name is in the right list. This is invalid because the process name can be set arbitrarily. Fourth, there may be an attack path that can bypass the access control. For example, as shown in the figure, we have 5 paths to attack the target. And if the target has access control, then path 1 fails. But among the remaining 4 paths, there may be a valid attack path. And this is beyond the reach of the target itself. The CVE 0346 is a real-world example. We can bypass the SELinux to achieve command injection. We will show detail in the case study section. Memory corruption vulnerability is common in parsing and processing requests, such as stack overflow and integer overflow. In addition, we use multi-threading to process requests. If synchronization measures are not taken, it may cause a UEF vulnerability. The CVE 0553 is a real-world example. It's a typical integer overflow vulnerability in parsing TLV data structures. It's using the total length to subtract the header's length to get the body's length, but the result can be negative, and when it converts to unsigned, it will become a huge number and result in quick overflow. The last is logical vulnerability. It's often caused by the lack of input validation. Most all UDS services have access control, so when you think your service will not be accessed by the untrusted application, you are likely to trust your input and directly use it. For example, the CVE 39616 is a command injection vulnerability in a network management daemon. The root cause is marked with the red box in the figure. The daemon directly uses the input to concatenate the command. An attacker can use this vulnerability to execute the arbitrary command. Next, my partner Yanhan will show some real-world vulnerabilities and demonstrate how to bypass access control. Thank you.
Hello, everyone. I'm Yan Han. Next, let me introduce our real-world vulnerability mining of UDS. And up to April 20th, we have found 12 issues in total, covered 4 well-known vendors, and got acknowledgements from 3 of them. Now, all the vulnerabilities are reported have been fixed by vendors. And in this part, we will make 2 cases to show that access restriction cannot solve all the security problems. There are restrictions in both cases, but we still have other way to bypass. The first case is a command injection that we found in log management daemon. With the restriction bypass, it could finally lead to an escalation of privileges from shell to system. The root cause is directly using the invalid input. The log module behaves like this. Before recording, the log management daemon will do such a check that whether the saving directory exceeds the size limit. So, some of the previously saved logs will be deleted. Such deletion is performed by command rmr here. And in this case, user can determine the saving directory. That means we can control the vulnerable log path here. So in consequence, we can inject a malware command into the CMD using separators such as semicolon. Since we have found the vulnerability, the next work is to study how to trigger the vulnerability. We found that movelogd daemon provides several log management commands through UDS for configuration, recording, control, and so on. So we should be able to trigger the vulnerability through UDS following the shown process. First, we set the size limit, and then we inject the malware command into the log path. And then we record logs several times to trigger the cleanup. And at that time, movelogd should execute the injected command. It's a real simple and clear process, but when we run the POC, we found that the UDS cannot be connected because SELinux blocks the request, and the logs show here. So the problem now is how to bypass the access restriction. And our idea is to find such a proxy. It should be allowed to access the vulnerable UDS service. And it should also have an exported interface, which can forward our malicious requests. Since the restrictions are performed by SELinux, we first analyze the SE rules to find out which domain can access this UDS. And we use the SE search tool, and we finally found that the domain platform app can connect to the UDS movelogd. So we have previously mentioned that there is a platform app named debugger UI. It is allowed to access the vulnerable UDS service. And even better, there is an exported broadcast receiver in the app to receive our log management commands. We can pass our log commands just through the broadcast to this proxy. So now there are 2 attack paths. First is directly connect to UDS and send our malicious payload to the movelogd, while the second is to send our payload to the debugger UI through the broadcasting, and then let debugger UI forwards to UDS. While the first path is blocked by SELinux now, while the second is a feasible bypass. We then write an exploit here as shown. We inject command who am I, and the result shows that we have successfully gained the privilege of system. So, in summary, we face problems when trying to connect to the UDS directly, but we found an upstream process that helped to bypass. And next is the second case. Case 2 is an auto-found right vulnerability we found in how. With the bypass of access restriction, it can be exploited to make arbitrary address right and could lead to an escalation of privilege. This vulnerability has been fixed by vendor, but it's not the disclosure date yet, so we won't mention any specific vendor and module name. And the root cause of the vulnerability is also the directly using a validated input. Well, this is very common in service that untrusted APP cannot access. The vulnerable daemon explores an interface for setting configuration through UDS. All the time are here. And in this case, user can determine the saving directory. That means we can control the vulnerable log path here. So in consequence, we can inject a malware command into the CMD using separator such as semicolon. Since we have found the vulnerability, the next work is to study how to trigger the vulnerability. We found that mobile logd daemon provides several log management commands through UDS for configuration, recording, control, and so on. So we should be able to trigger the vulnerability through UDS following the shown process. First, we set the size limit, and then we inject the malware command into the log path, and then we record logs several times to trigger the cleanup. And at that time, mobile logd should execute the injected command. It's a real simple and clear process, but when we run the POC, we found that the UDS cannot be connected because SELinux blocks the request, and the logs show here. So the problem now is how to bypass the access restriction. And our idea is to find such a proxy. It should be allowed to access the vulnerable UDS service, and it should also have an exported interface, which can forward our malicious requests. Since the restrictions are performed by SELinux, we first analyze the SE rules to find out which domain can access this UDS. And we use the SE search tool, and we finally found that the domain platform APP can connect to the UDS mobile logd. So we have previously mentioned that there is a platform APP named debugger UI. It is allowed to access the vulnerable UDS service. And even better, there is an exported broadcast receiver in the APP to receive our log management commands. We can pass our log commands just through the broadcast to this proxy. So now there are two attack paths. First is directly connect to UDS and send our malicious payload to the mobile logd, while the second is to send our payload to the debugger UI through the broadcasting, and then let debugger UI forwards to UDS. While the first path is blocked by SELinux now, while the second is a feasible bypass. We then write exploits here as shown. We inject command who am I, And the result shows that we have successfully gained the privilege of system. So, in summary, we face problems when trying to connect to the UDS directly, but we found an upstream process that helped to bypass. And next is the second case. Case 2 is an out-of-bound write vulnerability we found in HAL. With the bypass of access restriction, it can be exploited to make arbitrary address write and could lead to an escalation of privilege. This vulnerability has been fixed by vendor, but it's not the disclosure date yet, so we won't mention any specific vendor and module name. And the root cause of the vulnerability is also the directly using unvalidated input. Well, this is very common in service that untrusted APP cannot access. The vulnerable daemon exports an interface for setting configuration through UDS. All the configurations are saved into a global array, and which configuration to modify is determined by an index provided by user. So from this example code, we can see if here the v4 is 1 and there is no bound check for the index, then we can control the index to write out of bounds. We further studied how to trigger this vulnerability. The UDI service provides an interface for setting configuration. Here we can control 6 integers from param, known as CMD index v1 to v4. By setting v4, we can disable the check of the index. By setting index and CMD, we can control where to write, and v1 to v3 are actually written value. Then we know we should be able to write an arbitrary address by sending these integers to the UDI service. However, SELinux blocks the request once again. So we also have to find another attack path to bypass the access restriction. We first draw a communication flow diagram of this UDS, shown like this. Here, the daemon is the UDI service. It implements the function and communications with driver. And there is a hardware service. It provides an app interface for framework, helping the framework to indirectly communicate with the vendor daemon. And the framework also has an AIDR interface for application, help the application to indirectly communicate with the vendor daemon. So there are 3 attack paths. First is send payload directly using the UDS. And second, the process sends payload to the hardware bundle service. And then hardware bundle service forwards to the UDS service. And third, Untrust AP sends payload framework. The framework forwards to hardware bundle service. Then hardware bundle service forwards to UDS service. And in practice, the second and third attacks are feasible, while the first attacks failed to the Unix. So we can use the POC shown in figure to trigger outbound write. Figure 1 triggers by vendor. The POC is running as untrusted APP. And figure 2 triggers by hardware vendor. The POC is running with shell permission. Figure 3 is the crash log. And in summary, because the untrusted APP is generally unable to access the UDS service, the implementation security of the UDS is often ignored. However, access restrictions cannot solve all the security problems. In Android, the UDS service is usually a node in communication flowchart. Access restrictions can only determine who can access the UDS service, but cannot determine how upstream process use this UDS service. Therefore, a better way to ensure security is to improve its own security, rather than entirely depend on the access restriction. Okay, next part, we are going to introduce some automated analysis methods, which can help to improve the efficiency of UDS vulnerability mining. General mining steps can be summarized as follows. First, we should find the target and do the information gathering. And second, we do the vulnerability mining. And third, we should find a way to bypass the access restriction if it is necessary. So how can we improve the efficiency of these steps? Let's see the information gathering first. For UDI service, we need to gather in the socket information, process information, and the SELinux policy. Socket information includes namespace, type, and so on. And for file system socket, we also need its SELinux context. For process information, we may need the binary path because it is necessary for the reverse engine. And we also need the SELinux context of the process. Well, the SELinux proxy is required for attack path analysis. Fortunately, there are many great tools for information gathering. We can obtain enough information by combining existing tools. For example, SELinux rules can be exported by cat system fs SELinux policy by this command, and then analyzed by SE search tools. And we have combined these tools with Python and ADB. Here, the root permission is required. The figure shows a result of the tool. The tool can enumerate all UDI services on the device and list some basic information, such as the Linux context of socket file and process, the process binary file, and so on. We can use this tool to help us quickly find the UDI service. So for the second step, the vulnerability mining, it is more difficult to realize the automation. In white box cases, we can use various code analysis tools to improve efficiency, such as CodeQL and Suite. But for black box vulnerability mining, we still use traditional reverse engine because they are lacking a well-performed automatic analysis method. This figure shows an example of automatic vulnerability mining in white box cases. We use CodeQL to analyze the command injection vulnerability. We conduct a static chain analysis to find out whether there is a path that the data read from the received buffer flows to the system command. And CodeQL is very effective for code analyzing, as well as the static chain analysis. But there is a disadvantage that we have to model various library functions before using the CodeQL, because it is needed a lot of manual effort, especially when modeling some container class of the CVP. Okay, finally, the final step. If we have successfully found a UDS vulnerability, but if we found that it cannot be accessed directly by the Entrust app, and then we need to find another path to bypass the access restriction. And our solution is trying to draw a complete data flow diagram of the module. An example is shown in the figure. The data flow diagram contains many nodes and edges. Here, the nodes represent a process, and the edges represent different communication methods, such as binder, hardware binder, and UDS. Well, from this diagram, we can see which process communicate with other process with what communication method. Well, The key point of automation in this step is to automatically find both ends of the IPC. Finding pairs of a given UDS is quite difficult because kernel doesn't provide such an interface. But there are still some ways to try. To find which process can connect it to a given UDS, we can gather and analyze the restrictions by SE search. But the SELinux rules only tells us which domain is allowed, but not a specific process. So the difficulty lies in how to list all the processes that belong to a given domain. To find the owner and the user of the bundle service, we can use a tool named bindump to analyze. However, bindump relies on debug.fs, which is turned off on Android 11. So generally speaking, there are some analysis methods can be used to obtain the complete communication flow, but it is still very difficult to realize a complete automation. And in the end, we summarize our topic as follows. We draw some main conclusions that first, UDS are widely used in vendor daemons, and vendors often ignore their security because the untrusted APP cannot directly access the UDS. Well, the access control policy cannot solve all security problems. So it is very highly recommended to pay attention to the security of the service implementation itself, rather than depending on the access control. And for the vulnerability remediation, to dawn, all the vendors have worked diligently with us to remediate the security issues, and all vulnerabilities have been fixed and the patch are available. So we also have several future works to do. On the one hand, we need to future study the automated analysis method to improve our tools. And on the other hand, we notice that UDS service is not the endpoint. It is also an entrance to the driver. So we will go deeper into this path to see what happens. That's all for our speak. Is there any question?